Okay guys, so test number 5 is the direct comparison test, which it should sound familiar to you guys because we've seen it before back in the improper integrals chapter. We didn't focus too much on it then. There's going to be another spin on it in this chapter, but it's essentially the same thing. So we had videos on it recorded before, so you might want to go back and cross-check that one with this one, but it's essentially the same idea. So I'm either going to compare it to the sandwich, the top bread, the bottom bread, kind of like the sandwich theorem, or being inside a room and you're inside the room, you're the function, and then you have a ceiling function and then a floor function. Okay, and so what happens is you have to know that you're between the floor and the ceiling, and if the ceiling collapses, then therefore you collapse. If the floor somehow you're in a crazy wonderland and the floor rises, then you would rise along with it. Or I guess think of an elevator rising, you would rise along with it. So those two visualizations will help you guys to try to use the direct comparison test to make a conclusion about series that might sound familiar to you, but we can't make an exact, it doesn't fit into the mold of, say, what we're used to for a geometric series or what we're used to for a P series, but it's close enough to one of those two series for us to compare. So since we have an easy way to determine if geometric series are convergent or divergent, or P series are convergent or divergent, those two are the ones that we usually compare it to. And then sometimes on the AP test, they'll throw in a simple series that you guys can integrate using the integral test to then make a comparison to that. Okay, so there are certain parameters with this one that also has to be true. For the direct comparison to work, all terms must be positive. So when I'm plugging it in, all the values that I get for the terms must fall above the x-axis. So very similar to the integral test. So all terms in series must be positive. Okay, normally compared to, and same with the limit comparison test, compared to geometric and P series are the most common ones to compare it to. And then in parentheses, I'll say sometimes integral test. And I will do one example where you're comparing it to your series ends up being a Maclaurin series, one that's familiar to you, therefore one that we can compare it to. So you always compare it to something more simple so that you are able to answer the question. So we'll do 5 and 6 in this video. These are the common ones. And then in the next video, you'll watch the one on the last example here, which I think I skipped example 7 on this, but we'll call this 6A. And so we'll do a video on this as 6B. They're two separate examples. Okay, part 1 of this says that you have no negative terms. There's a ceiling function, which is going to be your series B with the general term B sub n, and then you have a conclusion that you're making. Let's say that so this is the one that you have the most information on, the one that it's either the geometric or P series that you have information on, and that happens to be the ceiling function. It's above you, it converges, so therefore if you're under that ceiling function and you're above the x-axis, you're standing, think of the x-axis as the floor, you're standing on that and it converges, therefore the ceiling converging means that you're going to converge or collapse to the ground as well. So that's the conclusion you're going to make. In part 2, you have no negative terms. You have a floor function, which is beneath you, and it's all positive values, positive terms, and you notice that the floor starts moving up. Well, what happens to you if you're on the floor? You also must diverge. So therefore, those are the two ones that you have to, that has to happen in order for you to use the direct comparison test. And also, there has to be a guarantee somehow that we know that you're either above the floor or below the ceiling. So that inequality that we establish must be true before we use the direct comparison test. And remember, that was it was the same exact thing you were doing with improper integrals. We just want to make sure that we're truly either above the floor or below the ceiling. Okay, so let's take a look at example number 5. You have that if I were to cover up, and I can use a white marker for this to show this is true. If I can cover up the fact that we have some type of series that looks familiar, but is not quite what we imagine our geometric or p-series to look like. So first, let's say we had this covered up so that we had just 1 over 3 to the n. We would notice that 1 over 3 to the n, well, that can be written as something to the nth power. If I factor out that nth power, it's the same thing as 1/3 to the nth. So if I ignore the +1 to try to figure out what I'm going to compare it to, that's what you would see. And so let's write it over on this side. So we're going to compare with, so this is going to be compared to not the integral, but the series summation notation 0 to infinity of 1 over 3 to the n, which again, we can rewrite this so that it looks a little bit more familiar to us as 1/3 to the nth power if we factor out the nth. And remember, 1 to the nth is the same thing as 1, so we are able to do that. Doing that, if I have something to the nth power, that's going to tell me this is geometric. So what do I know about this geometric series? I can conclude from this geometric series that since 1/3 is between -1 and 1, that this series converges. So this is what I know. In the back of my mind, I try to figure out what series I'm going to compare it to. I figure out if that series is convergent or divergent from what I know. And then the next part that you do have to do with a direct comparison test is guarantee that if this is the ceiling function and it converges, that you're below the ceiling function. So what does that mean? Okay, I have to show that what I'm actually trying to find the answer for, that's me, 1 over 3 n plus 1, that I am below the ceiling function, which I know converges. Okay, so 1 over 3 n plus 1, is this inequality true? Well, if you add 1 to the denominator of a function, then what happens is that that denominator is bigger, therefore the fraction is going to be smaller than this fraction, right? So let's think about it. A bigger denominator means a smaller number. So therefore, we've guaranteed or we've established that you are indeed below a ceiling function that converges. So therefore, what you can say is that by DCT, the series from n equals 0 to infinity of 1 over 3 n plus 1 is convergent by comparison to geometric series (1 over 3 to the n equals 0 to infinity). Okay, so now when we look at example number 6a, we're going to do something similar. Okay, if I ignore that constant value of +5, then I have 2 to the n, 3 to the n is the same thing as the comparing it to the geometric series 2/3 to the n. So I'm going to compare to 2/3 to the nth, 2/3 to the nth power. Okay, and so again, having to establish that 2/3 to the nth is convergent means that, and I'll write that out. So we know that this, and remember when we drew the bubble, we know that this is convergent. It's like you're keeping that in the back of your mind. That's a thought bubble. And then you're comparing it to another function. So in order for us, again, if that's my ceiling function, it converges, I have to establish that the other function is below that. So 2 to the n over 3n plus 5, is that less than 2 to the nth, 3 to the nth? And indeed it is. For the same reason, I'm adding 5 to a denominator, therefore that fraction is smaller. And so since this is true, what I can do is again make a conclusion by DCT to geometric series n equals 0. So what is it that you're comparing it to? The series must converge. So they're looking for, do you know what test you're using? Can you make a conclusion about the original series? So say the geometric series converges, therefore you then know that the series you're trying to find also must converge.